Hi everybody. With this lecture we are going to talk about how we convert our programming code into programs that the computer can actually run. We'll see the difference in the conversion. Now first of all, we'll talk about hardware for a second. The operating system provides software access to the hardware in an abstracted manner. So we don't just write directly to parts of the hardware. We actually write to the operating system, which then manages those connections for us. So the hardware always looks different. You never know exactly what kind of hardware your code is being run in. In this case, these are some truly ancient third-party wireless NES hardware that I picked up at a garage sale once. They're pretty fascinating hardware, and certainly the original designers for the NES did not imagine that eventually this would be plugged into it. Wireless systems, this is the very early days of wireless technology in terms of game controllers. So you never know exactly what the hardware looks like, and the operating system does that on purpose. Here is what the Intel X99 chipset looks like if you consider just the various bits and parts of the hardware on the motherboard. We can see at the top we've got our CPU, which is in this case was a Core i7, and it is connected to the PCI Express bus with a very fast connection. It also connects to RAM with a very fast connection, and that is one of the primary functions for this north part of this particular chipset. Then the Intel X99 chipset itself connects to various USB ports, the SATA ports, which is where your hard drives connect, more PCI Express ports for additional graphics cards or what have you. The audio connects into here, and the networking connects into here through all kinds of different buses. And then there's various management systems that you can use to track these computers on the network. Very interesting stuff. So the hardware here, these block diagrams, help us to know what kind of parts can we actually talk to from our programs via the operating system. Let's look at the processor at a little bit zoomed in view here. And a processor at its core has a set of registers that it uses to hold numbers, specifically addresses. And some real numbers in terms of integers and things like that, but for the most part it's addresses. It has a special register called the program counter, which merely contains the memory address of the next instruction it's going to read. So this is how it knows what it's going to do next. It always loads in the next instruction. It has a stack pointer that it uses to keep track of where the memory on the stack is. And that's important. We'll talk about virtual memory here in a moment. All these things connect to the actual execution circuitry, which is actually being driven by the program, step by step by step, just like following a recipe from top to bottom. This connects to the high-speed cache, which is a very, very quick, short distance set of memory that the CPU can use to store commonly accessed pages of memory. And then the high-speed cache connects down into RAM itself, which is much, much larger and a little bit slower. So memory is going to be arranged in an array of bytes from 0 on up. It's temporary storage. Certainly RAM and the L1, L2 high-speed cache memories are all temporary. It is much slower than the processor and the cache. So random access memory here is going to be slower than the processor's registers and the cache memory on the actual processor die. But RAM is much faster than disk, both in terms of reading in and out of it and in terms of randomly seeking information on there. There's lots of other types of storage devices that we can connect to the computer. Certainly the persistent storage devices are common and well known. The old school magnetic hard drives, which feature spinning platters and then a comb-shaped structure that rotates in and out and brings various read heads attached to these arms, brings them in contact with, or actually not contact, but very, very, very close to the magnetic spinning heads, and so it reads the data off. And there's multiple arms, multiple read heads, and multiple platters. It's a complicated device. We also have some newer solid-state drives, and solid-state drives are just basically, you can think of them as flash memory. They hold memory and they're non-volatile, so that means that the memory will stay on board even if the electricity is removed from them. The classic USB flash drives have really taken over in terms of non-volatile storage that's portable. A fantastic device. Magnetic tapes are definitely more old school. They used to be able to store what we'd consider a lot of data, a gigabyte or 10 gigabytes of data or 40 gigabytes of data. But nowadays, magnetic storage, in terms of having to run a reel around in a spool in order to get data off, is incredibly slow in terms of random access seeking. And also, they tend to decay and deteriorate simply because of the mechanical stresses put on the tape itself. All of these are slower than RAM, but they all do keep their memory without power, which is very valuable. Let's look at virtual memory. So virtual memory is an array of bytes where the operating system is using the hardware to create the illusion of unshared exclusive memory for each process. So each process thinks that it has all the memory, and it thinks that it starts at byte 0 and it goes on up to the largest possible address that the CPU can handle. It's unshared. Nobody else has access to this particular process. That's important. Process separation is one of the primary functions of the operating system. And the virtual memory tries to fool the process into thinking that it has unlimited memory. Obviously, there is a maximum address size, and there's also maximum storage sizes in terms of what the computer can actually handle. And so it might be able to address more than it actually has space for. When we run a program, the machine code, which is acted as binary, zeros and ones, each of these a separate instruction, in order for that to actually be run by the computer, it has to be loaded into memory. So to run that program, various systems within the computer through the operating system will copy the bits from whatever storage medium they're on and slurp it into memory. From there, it can be run line by line. Typically, well, they won't be run directly off the storage medium. They'll first be copied into RAM where they can be accessed faster. Let's take a few minutes here and talk about the organization of the program in memory. The actual implementation of this is kind of up to the designer of the operating system, but pretty much all the modern operating systems are going to use a scheme that looks like this. So we take a look, we zoom in here on the physical RAM chip, and we'll take a look at a section that has been reserved for a particular process, and this makes up the virtual memory for that process. And it's split into 4 major sections. Our code segment is going to be where the program instructions are actually stored. So maybe it goes from top to bottom or bottom to top in terms of the actual organization. That's up to the designer of the operating system, but they'll be read in sequence. So the next is the data segment, and the data segment is where various types of variables are stored in addition to the other 2. The data segment is split up into 2 primary sections. First of all, the initialized global and static variables section, and the uninitialized global and static variables section. The initialized section is further split apart into read-write and read-only. So we can have an initialized global variable that is in a read-only section, which means it is, you can think of it like a constant variable that we can access anywhere. It's global to the whole process. It can be read from anywhere. And we also have ones that are read-write. And those 2 things are kept distinct for purposes up to the program, and certainly the programming language uses those. We'll talk a lot more about that as we look at the C language. And then we have uninitialized global variables, which are stored in a different area. So they've been declared, but they haven't necessarily been given data yet. Our stack is where the automatic variables are created and destroyed, and where our process is storing the function return pointers. So the stack grows down typically, and the heap grows up. The heap is our dynamically allocated memory. Let's talk a little bit more about those 2. So the stack versus the heap. The stack is going to be storing our local automatic variables. An automatic variable is one that is automatically given space in memory as the program runs from top to bottom. So if we declare an integer, then that integer it starts to be used in the program. That integer, as declared as the program was running, is put automatically onto the stack where its value can be tracked. The sizes of these variables are specific, they're determined. The sizes of function return pointers are specific, they're determined, they cannot be resized. The stack needs to be able to push things on and pop things off and know that the sizes of all the various bits and parts aren't going to change. And the memory is managed efficiently by the CPU because the sizes of everything are consistent. The variable size then is being limited by that operating system. The heap, on the other hand, is where our variables are manually allocated in terms of memory that we're trying to allocate per variable. So the memory is unmanaged by the CPU, which means there can be fragmentation that can occur. You might declare 1, 2, and 3 separate variables, which might be initially assigned contiguously, but then if you pull out variable 2, it gets deleted. Then you've got a fragment. You've got fragmentation between the first and the third, and now the CPU has to deal with that. So the variable size is going to be unlimited, other than our virtual memory limits. And if you need to, you can actually get in there and reallocate the size of those variables. So because it's fragmented, because we can't guarantee the sizes of things, there are structures that'll keep track of how big everything is that have to be referred to when you get data out of it. So access to the heap is always slower than the stack. Not much, but a little bit. Alright, so how can we turn a high-level program like C++ or Java into something the computer can actually run? So we start with our source code that we've written. We're pretty sure the source code is correct, and let's assume for now that it is. And when we're all ready, we compile it into assembly code. And assembly code is difficult to read by looking at it, but it consists of the actual instructions that the CPU is going to follow. And it consists of loading instructions and storing instructions and adding things together and running various branching structures like jump and less than and equal to, that kind of thing. Once the assembly code has been created by the compiler, then it is assembled into machine code. The machine code is the binary code that the CPU actually runs. And it's no longer really human readable, though if you could read binary, you could go back and forth, because machine code is just a binary version of the assembly instructions that are there. So they're compatible back and forth. So most compilers, when we say, I'm going to compile my program, we really mean that we're going to compile, link, which we'll talk about in a minute, and assemble your source code all in one step. Though you can split those up for more control if you like. So the compile and linking process, we'll go into that a little deeper here. In C, our preprocessor expands macros and strips out the comments. So all these includes are expanded into the various files that we want to put into that file. Various constants can be defined and other things can be defined. We can even do the rudimentary if-then structures with an if-def. And the different forms of comments are all stripped out as well. The compiler is going to parse the code, meaning it's going to read through it. It's going to check for errors, and it's going to generate, once it's all happy, assembly language code. If the compiler process fails, you of course get warnings and errors that are shown to the user, but otherwise it'll go ahead and generate the assembly language code for you. The compiler then calls the assembler, which converts the assembly code into that machine binary code. And if you're compiling an executable, then the linker step is going to try to match all of the function calls that you've used to where the function code is. And they might be in different files, like libraries that you're importing in. For our purposes, we are going to be using the GCC compiler, the GNU C compiler, GNU C compiler. And the basic compilation options that we'll use is for the most part going to be we're going to be mostly using G and O, though we'll talk about the others here, and then the way to add a library. So the G switch lets us compile our program with debugging info that we'll need with the GDB debugging tool, and we'll do a lecture on that later. If we want to compile only without linking, we can do that with the C switch. If we just want the assembly code, we can use capital S. We can tell GCC to optimize as much as possible with the big O3, and I believe there's also O2 and O1. It kind of depends on the compiler. But optimization means doing things like take a for loop that's really short, and instead of trying to write all of the assembly code that manages a for loop, if that for loop is only going to run 1 or 2 or 3 times, then go ahead and unroll it and just copy that particular sequence of instructions 1, 2, or 3 times. If that's faster than the overhead involved in processing a for loop, then go ahead and do that. So those kind of optimizations can be done. The -O switch is the one you use most often, and it specifies the name of the output file. Otherwise, it just creates a.out every time you compile something. We can turn on all warnings, which can be annoying, but it's handy for trying to find errors and warnings that we wouldn't normally see. And then finally, we can add support for a particular library. So if we want to use the pthread library, then we do -L and then with no space, just pthread there, and that will allow us to link in a particular library. And these kind of switches should work with any of the UNIX command line C and C++ compilers. All right, so let's do a bunch of examples. So if we're going to compile an executable, if we have one source file, then this would be the simple command. So gcc is the program that we're invoking, and we're immediately going to use the -O switch to say what the name is, and our name here is dbtest. And then the file that we're going to use is dbtest.c. And here I've used the program name dbtest instead of something like test. And the reason for that is because if you create an executable, like using the name test, then if you create an executable that shares the name of a built-in program that's on the Unix computer already, when you try to run your program, it will instead run the built-in test, because your path directory or your path system variable, environment variable, is going to say look in /bin first before looking in the user's own directory. So make sure you use unique names that aren't program names that are already existing on your computer or in your folder. If you have multiple source files, then the simple way to do this is to have the first bit of our command be the same. So gcc -O to change the output name, let's call it dbtest, and then here's all of our C files, and that will compile it down into that one executable. If we have multiple source files, then the second way, which is our option B that's more efficient, is that we can compile them one at a time without linking, and then run the linker all together at the end. So this is really only important if you have a truly enormous program that we're taking care of. Otherwise, there's no reason to split this up. So first, we're going to compile all the source files separately into object files if we want to try this option B. So here's the -C option only, which compiles without linking. And then we will link all of the object files, the .os that are created, we'll link them all together to create the executable. And that we can do but with the same kind of command we had before, except instead of specifying the .cs, here we're adding the .os. And again, we're specifying dbtest as the name. Let's take a look at compiling and linking. So if we have in our C file dbtest.c, and inside here we're calling the function that we've created called db_create. That's a function we've created. When we compile this, here's our compile only step. We're compiling dbtest.c, the same one, and it generates dbtest.o. However, this particular function is not defined in dbtest.c. So we can't just try to compile this into something by itself and link it all up, because the linker will fail. Well, it won't be able to find the actual program or the function that we've created. Meanwhile, in dbcreate.c, we have defined our db_create function. And when we can compile that function file all by itself. Now we have a dbcreate.o object file. Now we can link together all of our object files, and we know that that is going to complete because we can access dbcreate that is defined in another file. And one of the keys here is that our main function has to be in one of these. And it doesn't really matter which one, whether it's in dbtest.c or dbcreate.c, but main has to be in exactly one of those. And the final dbtest program should then run. So library archives are a way to store a collection of object files together into a single large file, and it indexes them together to make accessing the various functions that are stored fast. And that's when we say access things fast, we mean from the perspective of the operating system trying to run the program. And it's usually faster than having to read every .o file. And this is going to be easier to link with if you aren't changing all of your library object files very frequently. So we don't want to have to relink everything if the library isn't changing. So to do this, to create the library, we'd first create all of our object files, as on the previous slide. And then we'd use the AR command, the archive command. Archive -R, here is the name of the archive that we're creating. And then here are all of the object files that we're going to be adding in. To use this, we would just go ahead and include it. Here's libdb.a. We could just include that alongside our dbtest.o object file as we compile the dbtest program. So these things can store all kinds of different files. And here's the Library of Congress down below in the US. Well, now for our final slide here, let's take a look at a full, complete C program. So this is Hello World, from compilation to execution, from creation to compilation to execution. So at the top, we'll go ahead and just cat out the file that we've already written. Here's our include standard IO header file, which is critical for us to use printf. Note void, so no return type for this particular program, so no return statement is used. And here's our main function, and it simply prints out hello world. Here's the compile. GCC -o HW creates the program HW, and then here's our .c file that we had looked at previously. Then we can run this whole thing, and note that when we hit enter on this, there were no errors, no warnings, no feedback at all. In fact, that's what we want. Then finally we run hello world with HW. Well, I hope that's been informative. That is how we convert our program files into actual programs that the computer can run. And stay tuned, and we'll talk at our next lecture. Thanks!